we saw how you make UTP, CTP, and TTP. But there are some salvage routes to making these nucleotides. Now, I have to stress that salvage is not the same as transport. You don't get something from the outside that's pre-made and ready to use, okay, to incorporate into your nucleic acids. Salvage is you get something like going to the junkyard and you try to take bits and pieces to make something that you want, so then you can put it in your car. It's kind of like this, literally, actually. So if you take a straight up intermediate with radiosuccinate, for example, which we have seen in the biosynthesis, this is uptake. This is straight uptake that is immediately usable in the pathway we discussed. That is not salvage. So with salvage, you have to do something else. You have to modify it a little bit before you can incorporate it to the pathway that we discussed. So for pyrimidines, you take stuff that the cell doesn't make them, okay, but they can use them if they find them around in the environment. And these are the various things. So the cell doesn't make cytidine or uridine, just the bases straight up. They can take them from the outside and you know, and then convert them, or uracil, that's the base. So it can use it, okay, in some ways. So to avoid some of the early steps in biosynthesis. So it's already coming with some goodies. You just have to modify them a little bit. A very common one is this one, uracil, okay, or uracil analog. So cells love to take uracil, and all you have to do then is to take a PRPP and make UMP, and you're done, right? So uracil will be used. It's a very common one. Now you can use an analog. Here's where the chemotherapeutics are coming to play. Instead of giving the cells a nice goodie such as uracil, and as I said, of all these things, uracil uptake and salvage is by far the most common one. So you give them something that looks like uracil, it just has a fluorine group, okay, and that will be 5-FU, 5-fluorouracil, an extremely commonly used chemotherapy drug. My wife was on it for 10 months, right? So what happens? So you take 5-FU, and it's actually a brutal component in the many chemotherapy regimens, because you take it for several hours when you are in the hospital, but then on the clinic, and then you come home with a pump, and you're in a constant infusion for like 2 days of 5-FU. So, but this is how it works. It's actually very cool. So 5-FU looks like uracil. It gets picked up. It gets incorporated in UMP, no problem. Okay, it gets phosphorylated, you know, and you get 5-UDP, which is by UMP kinase. And then goes on. Okay, so let's say it's time to make TMP, which is used in DTMP, which is used to make which is used for DNA incorporation, to make a deoxyribonucleotide, the T form. So you have to methylate it, correct? I mean, that was the whole idea. I mean, you know, you take the UMP, and then you methylate it in the reaction we discussed earlier, and you got DTMP, and then you can go on with the phosphorylation, and you can make DTTP. What if instead of DUMP, you have 5-FUMP, D5-FUMP? So then that enzyme, actually, thymidylate synthase, is completely killed by the analog that has gone through the reactions. It's ready to be used and incorporated into, into making and modified all the way to TMP. But at that very last step, okay, the enzyme cannot work, and you kill it. So you kill. So it went through all these reactions, right? From you, it went through this reaction, and then, you know, to get the kinase here to phosphorylate, you got all the way to 5-FUDP, and then it went through. Oops, you got the 2-hydroxyl reduced, but right here, but at the last step where it has to be methylated, This analog that has gone through has already been metabolized as a suicide inhibitor of thymidylate synthase. So extremely important, as I said, in chemotherapy used very broadly. So that's one. So it's a suicide inhibitor of thymidylate synthase. I told you that the HFR has to, the whole folate cycle, you have to regenerate it. It's the serine that donates the carbon on tetrahydrofolate to make the methyl tetrahydrofolate that is used by thymidylate synthase to give you DTMP, and in the process you generate back the hydrofolate, which you have to take it all the way to tetrahydrofolate before you can do anything with it. This is a DHFR enzyme that gets inhibited by some very old drugs, aminoterin and methotrexate, and all these things, the three of them together, you put them together, that's the original cocktail of chemotherapy used in the 50s by Sidney Farber to treat for the actually late 40s and 50s to treat for the very first time a patient with leukemia. The patient's name was Jimmy. He was a kid, and many of you may have heard Jimmy Fund. The Jimmy Fund, which started very many decades ago by the Dana Farber Institute at Harvard Medical School in Boston, which bears the name of Sidney Farber. And again, it has a very special history, place in the history of chemotherapy, these combinations, and this is exactly the metabolic pathways we're talking about. And by the way, these compounds are still used today, right? It turns out methotrexate has some very useful properties. At low doses, people take it for other settings that you need to inhibit cell proliferation. What could those be? Psoriasis is one, right? So it's inappropriate cell proliferation of the epidermis, of the epidermal cells, and you can take that drug at much lower doses than anti-cancer here. And it's extremely beneficial. People with rheumatoid arthritis also take methotrexate. What is rheumatoid arthritis? You have inflammation and hyperimmune response to the joints. Again, anything that works as chemotherapeutic at the appropriate dose can also be an immunosuppressant. And vice versa, anything that works as an immunosuppressant at a higher dose can also be a chemotherapy drug. So these drugs have been around for decades and decades, and they're still at the forefront. So you may ask, okay, what's the catch then with cancer therapy? There is no progress made. No, why are they still used? There's a huge amount of progress that has been made. People use them in different combinations, in different settings, and they are still the first-line drugs, okay, for treating cancer, various cancers. There are more. They come in many different ways: acyclovir, cytarabine, AZTs, capecitabine. My wife has taken that one too. This is a nucleoside analog, much in the same way we discussed. And here's the interesting part, right? These names, oops, let's go back. You may have heard of acyclovir and AZT. This is part of the cocktail until against HIV, okay, AIDS. So people that take the cocktail of drugs today to survive, HIV infections, and basically convert to a chronic disease. Not they can live for decades, forever, or normal life. These drugs were used originally, in chemotherapy. Now they are used as antivirals because what does the virus have to do to cause damage? It doesn't eliminate the virus, but in order to proliferate and expand in your cells, it has to replicate its genome, right? So anything that needs to replicate their genome is potentially sensitive by this metabolic interventions in nucleotide biosynthesis. So you see the enormous public health use and value of these compounds and these pathways.